Oh, I got called today. Have you been reading about these IRS scams? Like people trying to steal your tax money or something like that? You need to have your boy Trump fix this. Okay. Well done in New York, by the way. Did you get all the delegates?
I think 89 of the 94.
Okay, nice. Yeah, so I get this phone call. It was like a recorded message, like a computerized recording saying that the IRS has filed a lawsuit against my name or something like that, and I figure, okay, tax time, is something weird happening. So I called the other number back, and this guy couldn't speak any English, and but he has like all this information about me, like my address and my name and everything. So he asked me for like Social Security. Now I wouldn't give him my Social Security number, and I say, this sounds like a scam to me. He said, no, Mr. Mike, Mr. He's telling me something like it would go through the internal revenue payment option. He's like, he's trying to give me this address that had a bunch of numbers in it. So, yeah, I read online that the IRS will never call you by phone. They do snail mail.
Smoke signal.
They use smoke signal. On a CS note, I posted I don't think the link takes you right to the thing, but there was a show I watched yesterday. It's on on Netflix. What's up? No, actually, unrelated. But the show is called American Genius. And I've only watched like 1.5 episodes now, but the very first episode is Steve Jobs versus Bill Gates. And the premise of the show is it takes kind of historical, geniuses that are part of the creation of, what's happened in America, I guess. And but it dramatizes the story. So it's like a 42-minute show without commercials, basically telling the Apple Microsoft story from the beginning.
Is it accurate though?
Yeah. Yeah, and well done. Yeah, I mean, not even embellished. I mean, it's well done. So it's done like a documentary, but it actually acts it out. It has 2 actors that kind of look like the people, and then it has like some industry experts that are actually commenting on the things that were happening. I mean, definitely worth 42 minutes of your time. I thought it was. And the second one, I'm like halfway done watching it. The hot tub timer went off. So, it's the Wright brothers versus some other guy that was designed some sort of. No, actually, it's the guy who created the ailerons for the planes. So, yeah, it's kind of an interesting. It's equally interesting. So I learned quite a bit just watching those 2 things. There was actually an interesting fact that I learned that I wasn't necessarily aware of. So when Steve Jobs came back to, it makes sense now, but when Steve Jobs came back to Apple, when Apple was basically failing, I had always thought that Steve Jobs basically personally funded Apple to fix them. Well, this was at the same time that, and I've confirmed the fact since I saw it on the show, but this was during the same time that Bill Gates was going through an antitrust monopoly thing with them from the government, that Microsoft was a monopoly. Well, so Steve Jobs calls up his old nemesis / buddy / nemesis, Bill Gates, and says, hey, we need financial help. And, wouldn't you rather, given your current situation being accused of running a monopoly, wouldn't you rather have a competitor on hospice than no competitor? So basically Microsoft, I mean, for lack of a better term, they extorted money out of Microsoft to keep Apple afloat, so that Apple would still be a company that couldn't really compete.
Did you never watch the Ashton Kutcher one?
I have. I've seen it.
He was in there.
Yeah, but it was portrayed differently than that. I thought. They didn't connect all the dots for me, at least. Yeah, the Ashton Kutcher one I thought was Kutcher. How do you spell it? How do you say it? Kutcher, Ashton Kutcher. Am I saying it right? Well, Matt Kuchar is a golfer. He's way more important in Ashton Kutcher Kucher? Kutcher. Kutcher? Who?
Kutcher.
Kutcher. Yeah, he's like not even, he's barely in my top 10. All right.
10 for what?
Like overall.
Ashton Kutcher's?
People whose names start with Ash and end in ton. Emphasis on the ton. All right, so we were supposed to look at protecting our number of connected clients with a semaphore for today, right? Relating this to the quiz, why does this guy need protection, first of all? So why do we need to protect this value right here, effectively protecting this piece right here? Why does that need protection?
Because of Netflix and chill.
Okay, why does it really need protection?
It's the critical section.
Okay, what makes it a critical section?
Because it's incremented there.
It's incrementing the client number. So if a client connects at the same time as someone else sends a message, they will not receive that message.
Okay, so
we have to protect it so that if there is a race condition, the client gets added to the list, and then the message gets sent out.
okay, so generically, other quote people are interested in that value, correct? So that value is important to other entities, I guess. So with that in mind, who's actually this is the chat server, and is this happening before we fork, right? So each child here is going to get a copy of the current state of this guy. All right, so we still need to get this up in shared memory, right? Because we need this in shared memory. We also need the actual list of connected clients up in shared memory. But we need to now protect that shared memory. So we have kind of two layers here. So we have this guy being shared among all of our connected clients, or all of our client server children, let's say. And then we also need to make sure that nobody's allowed to read from this value while it's being changed. Okay, so those child processes are reliant on the accuracy of this current value. Right, so we need to protect it whenever that value changes. Now, because only when the value changes is it in need of protection, right? So the child processes, at this point at least, are never changing it. When might they change it in the future?
When clients disconnect.
Clients disconnect. So if a client disconnects and they change the number of connected clients down by one, doesn't that still break things for us? Because maybe the client that just disconnected lives at bucket 13, let's say, in our array. So now that client is no longer with us. He's decremented number of connected clients. Let's say number of connected clients was 20 and now it's 19. Well, that dude lived at bucket 13. So he really hasn't taken himself out of the equation, has he? How might we solve that? We're getting to that point, aren't we? So how would we actually solve our array containing the correct number of elements and only elements that are viable right now? So if I have a child process and this guy disconnects, so he's no longer should be part of our clients, our array of clients.
Have each child know what one it is. So maybe just assign that's its process ID or something like that, and then when it's done, say remove that index of myself.
Okay, so effectively remove an index. We have to write that. Yeah. Okay. What kind of values are stored inside of our client array? Integers. Okay, are they guaranteed to be positive integers? Yeah, file descriptors would definitely be positive integers, right? So could we create, could a client basically say, when I'm disconnecting, I'm going to find myself in the array and change that to a -1? So we're modifying that array. Would we want to treat that array as a critical section then as well, the change to the array? Make sure somebody doesn't accidentally send something to a file descriptor that no longer exists or isn't expecting messages? Sure, but we probably would not change the number of connected clients. So really, number of connected clients indicates the number of connected clients that have ever connected. Is that an accurate statement? All right.
So, what if they disconnected and reconnected? Would they go in the same spot, or would it?
No, it would be like a new connection,
Okay.
because they would be reconnecting to the original server that would then spawn off a new child. So you would get a new file descriptor.
So couldn't that array potentially get huge?
Oh, absolutely.
Oh, it could get to 1,000 and it would cut off.
Yeah, for us. All right. So what's the alternative?
Well, I mean, if you could have it that if the number of connected clients ever gets to say 800 or something, you go through and you clean house, you make another
You
array.
prune it.
Yeah. Put people,
Okay.
Put people that are still existing in the new array.
How would we handle it based on what we know about C right now? How would we handle effectively doing the remove at index? So in this case, if a client disconnects, we in fact would decrement number of connected clients. So we have one less connected client, and we would go through and instead of turning our FD into a -1, we would in fact remove ourselves from the list. How would we do that?
Couldn't you just, your position in the client array? Couldn't you just switch that with the last one that connected? So that, say you're in bucket 13.
Well, that's actually that's not a bad idea, especially if you're, the straightforward solution would be find where you are and basically switch that to a -1 temporarily, and then effectively just compress everything else forward. What you want to do is, since we're going to protect those two variables anyways, we can protect it with a semaphore guaranteeing they aren't going to change. You want to take wherever we are and the last dude that connected, swap those two values, and then decrement by 1. That's a pretty good solution, actually.
The only problem is if you had some reason that you wanted to know the order people connected in.
Yeah, because then how does the one that you swapped with know what its new position is unless that doesn't matter?
No, it wouldn't matter.
Well, it would just have to know what its file descriptor is.
Yeah,
Yeah, it has the
Yeah.
same file.
Yeah, so you're right. So unless, can we come up with a scenario where we would care the order in which they connected? You're right. If we did care, if we did need to keep track of that, that solution wouldn't work. But in terms of an efficiency perspective, rather than, let's say there's 500 connected clients, and we just removed client number 3. So that means we're, shifting down 497 clients in an array versus swapping 2 integers and decrementing a value.
I feel like the only reason that it would matter if you need to know the chronological order they connected in is if you start kicking people out based on how long they've been in.
Yeah.
You can only stay in for 5 minutes.
But the thing is, normally you'd think in chat servers, it's first come, first serve. So the first people in, obviously stay there, and then once they eventually get off, then new people can come in.
Yeah.
It's like you're playing a game on a server. Eventually it gets cut off, and then once someone leaves, you can join in.
Someone off that's already
Okay. Okay, well, so let's go this route. Let's say that we wanted it to be,
Yeah, because if someone's in a conversation right now, then and there, and they're the first one on, and then someone else tries to join, you can't just kick them off.
right.
You'd have to say server full. Yeah.
We could, maybe actually this would be a pretty good programming exercise. We could create a linked list in C, do it in terms of structs, because we don't have classes, and then we could probably pull it off. I'm not sure we really gain any sort of efficiency though with that. I don't know. I kind of like your solution with the swap thing, because at least at this point, it doesn't seem like there's a great reason to know the order in which guy is connected. All right. Well, so in any case, do we kind of understand the purpose of these semaphores in terms of protecting something when it's changing? So whenever we have something that changes that other folks rely on that value, we need to lock it down while we're changing it so that nobody else can actually get the information. Make sense? All right, so let's go ahead and do that. The first thing we're going to do is we're going to go ahead and disconnect these two things here. So we're going to say number of connected clients there, and then on the next line we'll say number of connected clients plus plus whatever. All right, so instead of doing it in 2 lines, we'll just do it in 1 because it's only actually changing right here. Okay. Now, having said that, do we actually need to protect both of these things?
We just have to make sure that number.
Because this guy is modifying our client array.
Don't you want to do that after
You could. I mean, so interesting question. Does the order make a difference?
Yeah.
Does it hurt us to protect both of these? And the follow-up question, is there a need to protect both of these? We want to pay attention to performance to some extent. It's this guy that dictates how far into this array we might go, right? So we could do that and then add this at -1. Fair enough? Okay. Well, so we still have a potential race condition. Let's say that we lock down just that line with the semaphore, but we don't protect this guy. And in between, when this guy's finally released and we've executed this line, and we're executing this line right here, we technically think that there's one more connected client than there actually is stored. And all of a sudden we try to broadcast to something, to some quote file descriptor that lives at bucket number of connected clients right now that hasn't actually been set yet here. So it could be some random memory location or some crazy integer, it might just be a 0, whatever it is. It's not a trustworthy file descriptor. So with that in mind, do both of these actually need protection? Yeah, we need to lock both of these lines because 2 things are changing and those 2 things are coupled. Right? These 2 things are coupled together. They're reliant on each other, and we need to protect that. All right. So we need to wrap these 2 lines inside of a semaphore.
If you're wrapping both of them, can't you just go back to having that be 1 line?
Sure, you can. I mean, I'm not sure there's necessarily a difference, but yeah, if that makes you feel better, we can do that. Okay, so how do we create an initial semaphore?
We did it. Line
Semi
27.
block.
Oh, we already did it? Okay, so that's going to be our actual thing to block, right? And then we're going to initialize that memory location with a, this is option 0, right?
Yeah.
And then the maximum number of resources is 1. We can only have 1 connection at a time, right? This is initial value 0, maximum is 1. Okay, so how do we actually go about protecting this line?
Once you get to it, you have to wait until it's on. So
Okay, so what's our sem command for waiting? Okay, so sem_wait. And we have to give it the semaphore we're waiting for. Block. Like that. Say this again. Oh, the address of it. That's right. All right. So this is going to wait until we can effectively increment it, right? Okay. So let's assume that we can increment it. Now we get to this. How do we give it back?
Well, first, do you already have your include semaphore.h?
I don't know if I do or not. All right, so how do we decrement when we're done?
Sem_post. Same thing.
Okay, so this is incremented variable, but we're not going to be able to get past that line. This is our bouncer. We can't get past this line until block is effectively 0 right now. Okay, but that's an atomic action. So once we get past that line, we can now do this, and we know we're the only ones that can call that line of code. We're the only ones that can make that change. Make sense? All right. So this guarantees that only one guy can make a change at a time. Okay, so now let's go ahead and get our shared memory set up as well. We didn't do that last time. It's kind of where we left off.
So that limits so that no one can access the client array either, because you're
Technically not right now, because, and even it doesn't really even protect our number of clients. Because both right now, our number of clients and our client array in my code are local variables. So children get copies of those dudes. So fine, we're blocking this dude, but who cares? Nobody else is using the same variables. So we're going to need to bring these guys into shared memory, right? Okay. So how do we convert clients and number of connections to be variables that are shared through shared memory? Okay, so we need to do a shared memory get. All right. So what are our commands for shared memory? All right, so we need to, I don't know if we have both of those or not right now, but let's go check. We do not. All right, so we'll bring those two. Well, he probably does in his code. All right, so we'll bring interprocess communication and shared memory into ours. And then when we're creating our clients and number of connected clients, these two dudes, they need to be done in terms of shared memory, right? All right, so how do we make clients be shared memory of that size? Here's our shared memory get. We give it a key, so that's going to be the name of the variable, right? And then we give it a size, and then we can give it a flag. I think 0 is the default, right? Oh, IPC create for the first time, and then the children, when they go to retrieve it, can put in a 0 or put in a 0.
What we did previously was IPC create pipe 0666.
Oh, for the read write.
Yeah.
But in this case, it's going to be 0666. That's good. In this case, we actually would want to make it 0600. Oh, no, 0644, right?
But would it even matter?
Well, it wouldn't matter if they don't try to write to it. Yeah, but effectively, the children, well, actually they would. Because we've kind of spoken ahead a little bit and said that when somebody leaves the server, that they are going to need to adjust those things as well. So realistically speaking, we do need to have write access for the child processes as well.
Do we? Couldn't it send to the server that it was disconnected, and the server could do it?
Server's too busy waiting on new incoming connections. So if you have the data, you might as well do the disconnect, because you with our semaphore, we're protecting it anyways. Yeah, so I think the right way to do it is the 0666, and also Christian worldview way of doing it. Okay, so we're gonna do right here. When we first create our clients, let me steal. Let's see who's the culprit. Oh, Amish is copying my line. All right. So shared memory, get. Is that right? SHM get.
Yes.
All right, and then we give it a key as a string, right?
Key is a key underscore T, which probably is a string.
Yeah, so doesn't it look like
Well, which is IPC private in our previous one, in the 14 test where we did it.
So we said IPC private.
Yeah.
So we still have to have a name for the guy.
This
In order
is
to
the parent's-
retrieve.
The parent's ID is where the shared array began.
Let me do this here.
It's probably scrolling down.
Okay, this returns the identifier. Oh, it returns an int, so we would have that identifier, so it doesn't matter what we put in for the key. Okay, so what did we put in before?
IPC,
Underscore private,
yeah, it's all cap.
like that?
Yep.
All right, and then the next thing is size.
Yep.
So that's going to be that guy. And then the last thing is the IPC underscore create, because it just create like that, and then pipe.
Yeah.
To, what was the other one?
0666.
That. All right, so that's shared memory get for that guy. And this is ultimately going to give us integer to our clients. Actually, this is going to be a clients ID. That's what this is going to return, the position in there. So now we need to actually retrieve the shared memory to use locally, right?
Yep.
Let's go ahead and set up our number of connections while we're at it. So I'll steal this line. So int number of connected ID is equal to size of int, and then IPC create 0666. Right, so both of those guys will be size of integer. All right. Now we need to actually get the shared memory. So how do we retrieve, now that we've created those shared memories, how do we grab the actual array given the ID for these two things?
The array equals SHM.
Clients equals SHM.
All lowercase.
And then the client ID?
Yes, client ID, null and 0.
What I'm gonna look real quick what those options are. Schmat. Man. Schmat. This is shared memory ID, shared memory address. This is gonna give us the address, so if we already knew it. And then flags. Oh, this is allowing us, we can choose to get it as read only or something like that. So we didn't even need to, we can override the 0666 if we want to. But this is just going to get us it with the permissions that it was originally created with. Right? All right, so that's going to be for that dude. This is going to be for, this is number of clients ID. This dude. Okay.
Does that need to be in pointer?
Who?
The number of connected clients.
Oh, because this is going to give us an address, right? Or rather, this guy's going to give us an address. Is that what Schmat gives us? Ay.
Yes, it does.
All right, so that's fine. So this will be an int pointer for that as well. And then down here, when we actually use it, we're going to have to say star number of clients plus plus. Actually, that gives us the actual int. Is that going to work? Number of clients, that's the pointer to the actual memory address, and we're telling that to plus plus. That should work. All right, so since we made it a pointer up here, if we want to get the value that lives at that guy,
Then you have to change clients too.
yeah, we'll now that we're making everything shared memory, and it's not the clients, the children.
The client array right there.
Client array, this is the same as it was before.
It is.
That's a pointer. Yeah, an array is a pointer. Yeah, this guy we were just treating as a normal integer, but now it's actually a pointer to an integer. Yeah, so clients shouldn't have to change. All right, so we're listening. We'll get an incoming connection. So let's just make sure we have these guys set up right. So we have our two IDs here, and we're going to need those inside of child stuff. All right, so let's check these. So here's our client ID for the shared memory client array. Here's the client ID for, or the connection ID for number of clients. Here's our actual clients array that we're grabbing from shared memory. And here's our number of connected clients we're grabbing from shared memory. Down here in child stuff, we're going to need those same things, except we don't need, actually, I'm going to move a couple of things. I'm going to take our two IDs, and we're going to put them up top, so we have global access to them. These guys are integers. They're going to be shared when we fork a child, Abe. So we'll have access to them already. All right. Then inside of main, we'll go ahead and give ourselves access to our couple of actual shared memory segments. Similarly, we'll do that in child stuff so that our child threads have access to the same things. Okay, so now these are local variables inside of here. So now when we say shared, or when we say send message, actually, does this guy, he's not even going to need that, right? Child stuff doesn't need that. It's our other guys that really need that. So child stuff just prints out child stuff. It sends a message to the parent. This is from the server. It sends a message to the connected client, and then it waits to receive a message from the connected client. It's really our broadcast and send message guys that need something. So send message, actually send message doesn't. Send message gets the exact client ID it's sending it to and the message itself. But broadcast, this guy needs access to our clients. So we're going to go ahead and give ourselves access there.
Are we passing it?
No, we're just going to create it as a local variable. Because we already have the IDs as globals in this program, and those are ints. So fine, if we're the child, we got a copy of those, who cares? We have a copy of an int, and that's good enough for grabbing something from shared memory.
So do we want to take int num client out of that then?
We do. I don't know if we're actually calling it right now, but we also don't need to take in clients. We're just broadcasting a specific message. And who are we broadcasting to? We're going to go ahead and grab our clients. We'll grab our num clients. So this guy right here turns into star this. That is the value at number of connected clients, because number of connected clients is an address. And then we'll send to that client a message and then the string length of that message. All right, so kind of our last piece here to get this set up as we go back to our child stuff. Child stuff is going to get our receive message. So here's the maximum message size. Here's the server reply. Here's us actually getting that message. And then we're printing the message to our screen. But really, when we receive a message from the client, we probably want to go ahead and broadcast that message to everybody, right? So we'll go ahead and say broadcast, and this guy just takes in a message. So the message we received was server reply. And at this point, it'll broadcast to everybody, including ourselves. What we'll probably end up doing here is changing our. Actually, let's make it work right to begin with.
When you want to send to yourself, so you
For your assignment, it was to. We'll do that first, but then we'll update this guy so that we know who broadcasts, so we can omit sending it to that guy.
Well, won't you want that like in a chat server so that you see your response?
Well, you can see it to your screen right there. You don't want to duplicate it. You just type something, it's on your screen, and then you don't want to see it on your screen a second time. All right. So that's going to broadcast. Broadcast goes down here. Here's the message we're broadcasting, and it's going to grab our shared memory stuff and do its thing. But in here, we're not actually changing that stuff, so we don't need to protect it with a semaphore. We did protect it with a semaphore up here. Let's see what our server currently does. We listen, we get an incoming connection, we do what it takes to add that new client to our shared memory, protecting it. Then we spawn off, let me just get rid of that line right there. Spawn off a child. If we are the child, we're going to break out of here. This is our kind of check to make sure we're actually the child. The process ID is 0. Then we'll call child stuff. So this is effectively the code that the spawned off child does. So this guy prints out that we're in child stuff. So we'll do that with it. We'll go ahead and send the message to the child. Then we're going to receive a message and then hopefully broadcast that message to everybody. Okay. Receive message should already work. Okay, so let's make sure our chat server builds and stuff. Oh, we need to prototype it. That function changed nature. We have it prototyped at the top. Okay. Undeclared here. Oh, max clients. Okay. So when we move that thing up top, we have to move this guy with it. Because this guy is done, implemented in terms of max clients. Okay. It's delayed.
Oh,
Concordia internet died. All right. Just not constant. Oh, it wants those to be constants. Okay. Since we made it a global. Oh. Same thing's true down in our broadcast. Ooh, wait a minute. Where's that complaining? What? This is running like super slow. Yeah, it didn't save the previous thing I had. I had put int in both of these. Concordia's internet hiccuping.
No, it doesn't like the constant int either.
Why isn't it showing that that guy has
Did you
changed?
save?
I did.
Initializer element is not constant.
Guessing it's complaining about these guys, not the value that's returned. So we should be able to store these as ints. Probably is this guy. It wants to be a const. Although it complained about both, so I don't think that's it either. All right, this is shared mem get. Oh, it wants us to do it as maybe a hash defined. Okay, we can do that. So this would be, let's see if it's happier with that. Oh, way less happy with a lot of stuff. All right, well, we'll fix that next time. So here's the deal. So you'll have another homework assignment over the weekend, but if you go to the hackathon, you are excused from the homework assignment.
I can't.
That's fine. So don't go and do the homework assignment.
What if we Skype?
If you Skype
Yeah, just put me there. I'll Skype in.
the whole time.
Yeah.
When's the latest you can sign up for that again?
What do you guys think?
When's the latest you can sign up for it? Well, I guess I don't know. I don't know. I mean, you sign up on the website to like get your e-ticket or whatever. It's free. But if you sign up, shut up! If you sign up, make sure you let me know so I can add you to the list. If you need a ride from campus to there, then we're providing rides. If not, you can meet us there. But regardless, if you sign up, make sure you let me know.